Hello and good morning to everybody. So, today we will still continue with the tungsten enzymes, and today we will see some more examples where this tungsten can function as a very useful catalytic site, where this particular one, that means the site is attached to the ligand donor atoms. So, SS donor atoms were present, and there are two positions. It is not that it is exactly a hexacoordinated octahedral geometry, but is highly distorted geometry, where the substrate can approach to the metal site in search of the reagent to be attached to the substrate for a typical conversion. And for the first group of those molecules, what we have seen, the first group of molecules were dealing with aldehydes, and these aldehydes, when they are involved in some form of oxidation and reduction reaction, that means a family of these metalloenzymes, what is known as AOR family, aldehyde oxidoreductase family, and that family basically used for handling the oxidation of aldehydes, and in some special cases the tungsten center can be utilized for the handling the corresponding oxidation of formaldehyde also. And during that redox process, that means if we just consider that aldehyde is getting oxidized to carboxylic acid, and we are just interested to know how this particular oxygen coming to convert this particular substrate molecule, which is our aldehyde molecule, and whether these oxygen atoms are coming from water molecule or the dioxygen present in air. So, this particular thing, when we go for the second one, that means the second family of these tungsten bearing enzymes, these are the second family consists of the formate and N-formyl methanofuran dehydrogenases. So, the second group basically will be working on the formate. So, formate is HCO2 minus. So, it will be working on the formate anion, and we just can examine for the elimination of CO2 from the formate. And some other thing is also there, that means if we have a furan substrate, and if we get furan is attached to some methyl group and some other aldehyde function on the furan ring, if those are handling, because these are very useful biological fragment which can take part in different reactions. So, that gives rise to N-formyl methanofuran, which is utilized for their corresponding dehydrogenase activity. because these biological molecules are very important, but still again we are handling either the formate or the formyl function. This is nothing but the formyl function attached to the furan ring, and that furan ring is basically utilized for this particular, that means other groups are also attached to the molecule, and that is utilized for several important biochemical reactions. So, these things, that means the formate and the substituted furan derivative, they are basically utilized by the tungsten containing enzyme, because sometimes in physiological condition they go for fixation of CO2, that means carbon dioxide fixation. So, carbon dioxide fixation is a very useful chemical technique where we can convert the carbon dioxide, which is basically polluting our environment, and that carbon dioxide can be inserted to some important biologically important molecules, and those molecules can be obtained through this formate and N-formyl furan derivative, giving rise to the formation of acetate and N-formyl methanofuran respectively. So, N-formyl methanofuran is the thing which this particular dehydrogenase is basically working on some substrate, and the result of that thing is the N-formyl methanofuran formation. Because these methanofuran derivatives are very useful reaction for the formation of methane also, because once we get this particular thing and attach to some furan ring, and if this is coming, that means this formyl derivative, if we can get it from carbon dioxide, and ultimately if we can convert this formyl derivative to methane molecule, then this is a 1 carbon derivative, this is another 1 carbon derivative, but attached to some bigger molecule, and ultimately it is converted to the formation of the corresponding methane. So, the bacteria, the methanogenic bacteria and all other groups of molecules or enzymes which are useful for production of methane can be known if we can little bit understand about the role of these tungsten enzymes or the tungsten centers for handling this carbon dioxide formation of the formyl derivative and the generation of the methane molecule. So, this methanofuran therefore forms a family of chemical compounds. So, this is a group of useful chemical compounds. We do not study all the time much about these methanofuran molecules, but they are useful molecules and they are also found in methanogenic archaea. So, methanogenic archaea is therefore useful for handling the methanofuran derivative, and that methanofuran derivative can be utilized for the production of methane. So, the methane production is therefore dependent on the tungsten center. If the tungsten center is utilized for handling all these molecules. So, this methanofuran basically converts the formyl methanofuran in an early stage of methanogenesis. So, methanogenesis is a pretty complicated reaction, and in some cases the formyl methanofuran formation is taking place, and the enzyme formyl methanofuran dehydrogenase, what is we just discussed, that it is there, formylates the methanofuran ring. So, it is useful so for the formylation reaction also. So, the formylation reaction is taking place using CO2. So, any formylation reaction whether we can go for, because formylation reaction is also a very good reaction for organic transformation. So, formylation reaction, if we can do using CO2 as the sole carbon source. So, utilizing CO2. So, nature is always overburdened with the CO2 molecule, that means the carbon dioxide gas, and the environmental pollution, the global warming and all these things are dependent on the amount of carbon dioxide in the atmosphere. So, if we can fix that, so it is basically the fixation reaction. If we can fix that particular carbon dioxide in some useful organic transformation reaction, so we call it as a fixation of CO2, and this CO2 is our very useful one carbon source for organic transformation. So, this one carbon source is basically utilized for the formylation reaction, which is a very useful reaction for the transformation of the different type of molecules. Because in laboratory, what we can do in laboratory, if we have a phenol derivative and if it is force substituted one, we cannot do any transformation, that means the formylation reaction on this carbon or the formylation reaction on this carbon cannot be achieved using carbon dioxide. So, these biochemical pathways are therefore very much useful to know whether we can also use those enzymes for the formylation of any useful molecule. So, this formylation cannot take place using the source for that formyl group as carbon dioxide, but can be done using urotropin, which is nothing but hexamethylene tetramine, and that hexamethylene tetramine is utilized for the insertion of CHO group at position 2 and another CHO group at position 6. So, when we have force substituted phenol and some laboratory technique is there, this is a laboratory technique for formylation, we get the 2,6-dialdehyde molecule. So, substituted dialdehyde molecule whereby insertion of two formyl groups on the benzene ring give us the product around this particular phenol OH function. So, when the enzyme, the formyl methanofuran, so basically we are talking all these cases, the transfer of the formyl group from one molecule to the other, and this particular formylation reaction is useful because this formylation is taking place using another enzyme which is formyl methanofuran dehydrogenase using CO2 as the source of carbon. So, we basically fix the carbon dioxide molecule to some useful organic substrate, and all these molecules like this handling this methylofuran derivatives and all these, they structurally they are analogous, because whenever we study these tungsten sites, we all the time we side by side we try to compare it with that of our molybdenum site. So, this is very much similar to that of well known and well established molybdenum site for formate dehydrogenase and nitrate dehydrogenase. So, these groups of molecules, how the molybdenum is attached to the oxygen and the sulfur donor atoms, and how the redox behavior on the molybdenum center is taking part, and whether the cysteine or selenocysteine residues also can take part for these useful transformations related to the coordination. So, these are all related to the corresponding molybdenum enzymes, and in the oxidized form, when the metal center is in the +6 oxidation state, we get the species as the corresponding coordinated environment. This tungsten, so we have one L over here and another L over here. So, directly we can just compare with the molybdenum site, because the molybdenum also has a bidentate ligand here and bidentate. So, this is L and this is the second L. So, L2 is there, then tungsten is in your hand, then we have O and the X. So, this O is there, it can be double bonded O or it can be OH function, and some X group as chloride or some other group is also present, and molybdenum is stabilized in the hexavalent state. And this particular case, when we see for this family of enzymes, when we have the formate dehydrogenase, again the CO2 is our substrate and this CO2 substrate is utilized for the transformation. So, when we have that formate dehydrogenase, which is FDH, and first time it was identified as this is the one particular enzyme where instead of molybdenum we have the tungsten center, and formate dehydrogenase is basically the corresponding transformation of this CO2 molecule to the corresponding formate anion molecule and is a reductive pathway. So, how we can go for the corresponding formate generation, and this formate generation is another pathway which we just now we have seen, which is related to the formylation reaction, and that formylation reaction is solely dependent on the species carbon dioxide. And here also the generation of the formate is also dependent on the CO2 source. So, interestingly, in one particular case, because this is a very important and the vital reaction which is related to the human respirations, to all aerobic respiration, where we basically burn the system, the carbon related fuel or the carbon related foodstuff is oxidized to carbon dioxide. So, handling this CO2 molecule in two different ways, and is basically when we convert this CO2, the formate is basically a reaction where we need both proton as well as electron, which is a 2 electron reduction step, and one proton is also utilized. So, that immediately gives us some important clue related to this particular tungsten center, because this 2 electron process, we know that this 2 electron process can be achieved if we have tungsten in tetravalent state and tungsten in hexavalent state. So, basically this can settle between these two oxidation states. So, just simply change in oxidation state of the metal center can supply the electron, and we can have some other source. It can be our iron sulfur clusters, ferredoxin clusters, or it can be some other biological reductant like NADPH, etc. So, when these ferredoxin molecules are present, as well as some NADPH molecules are also there, which are well known biological reducing agents, because we have to supply this particular electrons, this number of electrons to the system, such that we go for the corresponding reduction of the CO2 molecule. So, these things are available, but the choice is dependent on the corresponding reduction potential. So, the E0 value, the redox potential value or the half wave reduction potential value for NADPH and iron sulfur cluster will tell us that which particular potential we can reduce for the catalytic cycle, at which particular potential we can deliver these 2 electrons to the hexavalent tungsten site, such that this hexavalent tungsten can be reduced to the tungsten 4 site, and if the particular one, if the total reaction is a 2 electron transfer reaction, but if some catalytically active intermediate is formed there. So, if that intermediate is present, which is a typical metal ion center, that means the tungsten center having intermediate oxidation state, that means tungsten 5+. So, these 2 electrons cannot be delivered at a time, that means the tungsten is not jumping, is not moving directly in one single step, that means it is not a complete 2 electron transfer process such that it goes down to tetravalent state immediately when it reacts with either ferredoxin molecule or the NADPH molecule, but it can go through the intermediate oxidation state, that means the pentavalent tungsten state. So, this can be nicely detected. So, the detection of this is possible, and if this detection is possible, we can immediately say that this tungsten 5+ is involved for the catalytic cycle, and it basically obtained from 1 electron reduction of the hexavalent state, and finally, when we get this corresponding format anion with the help of the 1 proton also. So, there is also some site where the proton is also attaching to the substrate molecule, and we get back this particular molecule to the corresponding hexavalent state. So, the reduction reaction, that means the reduction for this particular reduction is very important, and what we see that if we have large number of these tungsten molecules in hexavalent state, but all these molecules cannot have the same E0 value. So, that is why the importance of the primary ligand donor atoms are useful. So, depending upon the nature of these ligating groups, so the nature of these of the ligands do basically control the corresponding E0 values. So, if we have the corresponding E0 value for this particular site, which is matched with that of our corresponding biologically available reducing agent, then only we can settle between these oxidation states, and tungsten is very useful center for delivering these 2 electrons required for the reduction of carbon dioxide to format anion. So, when people discovered these things and they try to identify that when we are settling between the 2 oxidation states, that means the tetravalent tungsten and the hexavalent tungsten, but in the physiological condition, some reducing agents definitely be there, and which is nothing but our NADPH. So, NADPH is the corresponding physiological electron donor for reducing the tungsten from the highest possible oxidation state, which is +6, to the lowest one, which is achievable in this particular medium, which is the tetravalent one, that means tungsten 4+. So, we have the bases, we have the sugar unit, and then we have the phosphate backbone for the nicotinamide adenine dinucleotide phosphate, and this particular one is useful because it has a typical redox potential, and it has also some positions, because that is why we are writing as NADP and NADPH. That means during electron transfer it can also supply the required number of protons, because sometimes we find that though we are doing a corresponding reduction reaction in water medium, but the required number of protons are not available, because all these E0 values what we are measuring, say in aqueous medium. So, in aqueous medium, when we are measuring by some electrochemical technique to determine the E half value, we expect that in aqueous medium there are plenty of water molecules, and the medium is also buffered. So, at suitable pH value only it can either give rise to the corresponding number of protons, or it can accept the proton also. So, the transfer of electron, whether the electrode is supplying the electron or the electrode is taking up the electron, is also dependent on the availability of the proton transfer. That is where we can have a corresponding electroprotic equilibrium. So, for that electroprotic equilibrium, we always think of that whether this particular thing is also going for deprotonation, and when deprotonation is taking place, our E0 value is also getting lowered. Is a typical example. We all know that whenever we have a CONH backbone from a polypeptide chain. So, this CONH backbone for any polypeptide chain, and we all know that this amide function or these oxygen donor atoms, but this is a weakly coordinating center, but this is a better corresponding donor center for coordination to any metal ion. So, in this particular assembly, that means the amide function is attached to the metal side. Whatever we get is that we can measure the corresponding E0 value for this corresponding oxidation reaction, say. So, if we are going to monitor the corresponding oxidation reaction, we expect that some potential value is there where this hydrogen is attached to the amide nitrogen. But if we can add some base, and the base is taking up this as the proton. So, H plus is removed by the base, and our amide function is functioning as N minus. So, charge density is more, and more effective charge transfer to the metal center is there, and we get basically a lower oxidation potential for any kind of oxidation reaction what we are studying for this particular metal center. So, if this potential is also matching for the corresponding E0 value for the dioxygen molecule which is present in the air, so that can immediately oxidize this particular metal center to the higher level through the deprotonation of this particular amide function. So, this is a very useful and a natural tendency for these transformation reactions. So, this particular one therefore is a very useful physiological electron donor, because it can supply not only the electron, but also it can supply proton for the redox reaction. So, we can have two different types of reactions, what we call therefore, that if some reactions are there for the reversible transformation of carbon dioxide to formate and formate to carbon dioxide, and that NADPH is involved. So, if it is dependent on NADPH, so this is our NADPH, so phosphate NADP phosphate backbone is also there. So, if it is dependent, so this is the oxidized form when we do not have the proton, that means when we oxidize this, one proton is also lost, the way we have seen just now, that when amide group is coordinating and we are trying to oxidize the metal center, the amide function will have a natural tendency for deprotonation. So, similarly, the formate is therefore is getting oxidized by the oxidized form of nicotinamide adenine dinucleotide phosphate to carbon dioxide and NADH. But if we want to get the corresponding reverse reaction, that means if we want to fix the C1 source, 1 carbon source of organic matter, that means the carbon dioxide can be fixed as the formate anion, then the reaction should be with the reduced form of the NADPH. So, reduced form of this will react with this in presence of the tungsten based enzyme for the conversion of CO2 to formate. Same thing also happens if there are some other group of enzymes available, where the characterizing the characteristic E0 value, which all the time I am telling that this is important. The E0 value for the metal enzyme site depending upon the corresponding environment of the enzyme. So, if E0 value is not matched with that of our NADPH, it can go for searching some other biological reductant or other biological reducing agent, such as this ferricytochrome B1, which is nothing but a porphyrin ring, is B1 type porphyrin ring attached to the iron center, and when this iron center is in the ferric form, that means the +3 oxidation state, we get ferricytochrome B1. So, this ferricytochrome B1 in its oxidized form, which is like that of our oxidized form of NADP plus. So, this can oxidize our formate function to carbon dioxide, and 2 of these ferric cytochrome B1 is reduced back to ferrocytochrome B1. So, this particular case is settling between the change in the oxidation state of the iron site or iron active site, which is present with the cytochrome B1 and with the elimination of the corresponding number of proton, because whatever proton is eliminating from this particular reaction, because this is typically the corresponding oxidation reaction, and this oxidation reaction is associated with the elimination of the proton which is coming from the formate, but this ferricytochrome unit, which is basically a cytochrome unit where we have the macrocyclic function, and that macrocyclic function can have several donor atoms present, such as sometimes the carboxylic acid groups are present, but these donor groups, if they are not available for taking off the proton which is produced from the reaction, so this proton will be available in the reaction medium only. So, this proton can remain in the reaction medium as H plus, which is not directly attaching to the cytochrome site, like that what happened with that of our NADPH, because in case of NADPH it has also the corresponding proton demand for the corresponding electron transfer. But in this particular case, if we have the corresponding, in sometimes we have the carboxylate groups attached to that, But if the corresponding pKb value, that means the corresponding basicity value for the corresponding anions is not matching with that of our corresponding proton abstraction tendency, it will not go to attach this particular side chain carboxylate acid groups, it will remain H as H plus in the medium. So, we have two different types of reactions which can be achieved through the involvement of the tungsten enzyme. One is nicotinamide adenine dinucleotide phosphate dependent and another is typically cytochrome dependent. So, we see here that in one case it is dependent on NADPH, in another case in some of these reactions we have seen they are dependent on the iron sulfur proteins, and one more example here we are seeing that it can also be dependent on cytochrome molecules also. So, after the second group of molecules, we can now move for the third type. So, third family of these tungsten bearing enzymes So, this third family of these tungsten bearing enzymes is a very interesting type of enzyme which is known as acetylene hydratase from Pelobacter acetylenaceus. So, this particular enzyme is abbreviated as AH, which is not be confused with aldehyde. So, A stands for the corresponding acetylene, that means it is functioning on the acetylene unit, acetylene, and this H is for hydratase. That means it can put one water molecule to the carbon-carbon triple bond of acetylene, which is a very interesting reaction, how we can put the water molecule on acetylene and which is catalyzed by our tungsten enzyme. So, whatever oxotransfer reactions we have learned so far for the molybdenum group of enzymes and the tungsten group of enzymes, where we have seen that the very important reaction for these are our oxotransfer reactions. So, these oxotransfer reactions can be very easily managed by the formation of the corresponding oxo group or tungsten double bond oxo function by the involvement of water molecule, which is in the intermediate stage go for deprotonation to hydroxide ion and ultimately to O2 minus, which is for the corresponding oxo formation, oxo molecule formation, because both molybdenum and tungsten have a natural tendency to form a very useful double bonded O, single bonded OH or single bonded OH2 function around the metal center when they are also attached to some other ligating groups like the terene units. So, the terene sulfur groups are always there, and finally, we have the two vacant positions, the two available sites for all these reactions. So, therefore, once it is known that tungsten can handle this water molecule nicely, we can immediately say that this water which is attached to the tungsten site, say one water molecule is attaching to the tungsten site, which is not undergone any kind of deprotonation for hydroxido function or further deprotonation for the formation of the second oxido function on the tungsten molecule. But this water molecule, once we have this, we think that it has been activated, and this particular activation is much more when we have this particular tungsten site in the high valence state. So, the high valence state is always very important on the metal center for the relative activation of these. So, we have two lone pair of electrons on this water molecule, and these two water molecules, these lone pairs are donated. So, one of the lone pair is getting donated to the tungsten site, but still the polarization is not that big that we expect that there should be some deprotonation of any of these hydrogen as H plus, but it is getting activated. So, when we are getting activation for this, so activated water molecule having some electronic charge on it, then electrons are there, it has not undergone any kind of deprotonation for extra charge development, because this is there. When charge is developed, we have the hydroxide function, which is a nucleophile, well known nucleophile to all of us. So, this nucleophile can go. So, the reagent basically, so what we are just now we have discussed also that on tungsten center we have the coordination sites, and one is the substrate site, that means S, another is the reagent site. So, now this reagent is a pretty simple reagent which is well known to us also, that is this acetylene is our substrate now, and this water molecule is our reagent, and which is getting activated. That means, its nucleophilic character has been increased, and due to that change in the nucleophilic character of this water molecule, it can simply go and attack this particular acetylene site. So, these hydratase reactions are nothing but the attack of the water molecule to that acetylene site, because these reactions are well known for 100 years or so, or more than 100 years, this sort of reaction. That means, the hydration of acetylene molecule is well known, but it can be synthetically made in the laboratory in presence of the mercuric ion, and in presence of that mercuric 2 plus, your nucleophilic character on this water molecule is enhanced, and this can go and attach to this particular acetylene molecule. But the condition for any kind of enzymatic reaction is little bit a soft reaction, and in this particular soft environment, because the reaction temperature is very low, which is in the native condition, that means in the water medium and atmospheric pressure. So, everything is not very harsh condition for the transformation, but the presence of the metal centered enzyme basically play the important role for the corresponding hydratase reactions. And these hydratase reactions are not only very much effective on the acetylene, there are some other group of molecules are also known, because this particular reaction, that means the hydratase reaction, is a very well known reaction. And when we have iron site also, because some iron based enzyme has also been discovered and has been studied in detail also, where the corresponding substrate is not acetylene, but it can be a nitrile species such as acetonitrile. So, when we have acetonitrile in our hand, so that can also go for the corresponding nitrile hydratase reaction, but the metal center is different. That means, the same water molecule, the same activated water molecule can be dumped over this triple bond, and this conversion for this is different compared to the conversion what we expect for acetylene. So, when we have the enzyme in our hand and this hydration reaction of acetylene is therefore operating. So, addition of this water molecule on the triple bonded carbon CC triple bond of acetylene molecule. So, CC triple bonded acetylene molecule during the addition of this water molecule is immediately converted to acetaldehyde. So, this is the achievement, that means the entire water molecule has got inserted within the acetylene system, and this oxygen of the water molecule is now has been converted to the corresponding aldehyde function of the molecule, and like that of the corresponding transformation, that means we immediately get another function, that means this is acetylene and we get the corresponding acetaldehyde molecule. And when it is catalyzed by this AH, which is definitely a different reaction type, which is different from the oxidoreductase type of reaction, which is well known for all molybdenum bearing enzymes and all tungsten bearing enzymes, that means the tungsto enzymes, where the oxo group is formed and that oxo transfer reaction is very nicely taken place. But here we have the activated water molecule instead, and that activated water molecule is going to attach the corresponding triple bonded CC unit of the acetylene molecule. So, this is the third type of this enzyme, is little bit different from the other tungsto enzymes, because this acetylene hydratase can be isolated in air, although from an anaerobic bacterium, because this is not available for the aerobic bacterium, but this is available in the anaerobic bacterium and is moderately stable in aerobic conditions. So, when we go for some aerobic condition where we have plenty of dioxygen molecule is available, so that plenty of dioxygen molecule is not interfering with any kind of this transformation reaction and is stabilized in some dioxygen environment, and it shows the corresponding hydration reaction of acetylene. And what we can understand little bit, that how this reaction is taking place, we can go for the corresponding model studies, which is a useful technique for all that inorganic chemist, the synthetic inorganic chemist who can handle these systems for the different model reactions. So, the model compounds the model compound approach, what we call it as a model compound approach. That model compound approach is very useful, that we take a typical model compound in our hand, and if it is a tungsten related enzyme, so any kind of enzyme can be examined in that fashion, that we have the tungsten centered one. So, if we can have, that means the mimicking the corresponding active site what is available in the nature or in the biological system, that means what we have seen so far, that the identification of the site, that means the metal ligand stoichiometry. This stoichiometry is when we have one metal center, we have two ligand discrete ligand system in the terene unit. So, for the model compound also we try to preserve the same donor atoms. If it is coming from tungsto terene units bearing two sulfur groups, in the model compounds also we try to put these two sulfur bearing units around the tungsten molecule, such that we get a tetracoordinated form of the tungsten. And then how we go for the different reactions for the generation of these X and Y. So, the availability of these X and Y, they can vary from the different units, like they can be sulfur, they can be SH, they can be oxygen, they can be OH or OH2, or can also be some selenium site. So, all these choices are there, and depending upon the other part which is going to attach on the tungsten, as well as the corresponding oxidation state, which is also important, that which particular state is basically involved for the catalytic function. So, when we talk about the tungsten site, and we do not know whether the hexavalent state or the tetravalent state is catalytically active. To make this model compound, that means the corresponding metal ligand assembly, we have the metal center as tungsten. So, what type of metal salt we should use? So, the choice of metal salt is important, and the choice of the ligand also, and whether the same ligand system can stabilize this tungsten site either in the +6 or in the +4 oxidation state, because it is not possible to have any unique ligand system such that the same ligand can stabilize the tungsten environment in both the two possible oxidation states, that means the tetravalent and the hexavalent. So, depending upon its corresponding stabilization, the electronic stabilization, the one particular ligand, if it is a diethyl type of ligand, but having a different backbone, basically all the backbones are different, it can either stabilize the corresponding model compound in the +6 or +4 oxidation state. So, when we get the compound in +6 oxidation state, that means the ligand can stabilize the corresponding model compound in the higher possible oxidation state, that means the highest possible oxidation state. So, ligand is well suited for the stabilization of the metal center in the hexavalent state, and the corresponding reduction potential, that means the corresponding reduction potential for the transformation to +6 to +5 or +5 to +4 is low. So, synthetically when we make in the laboratory this particular species as a model compound, we get the compound only in one particular oxidation state, and that immediately gives us some useful information that whether that compound which has been prepared in the hexavalent state is useful, that means it can show the corresponding catalytic activity. So, that next can be tested for their catalytic activity. So, catalytic activity for the hexavalent compound can be then scrutinized. But if we find that the compound which is prepared in the hexavalent state is not catalytically active, we should try to prepare the compound in the next step, in the pentavalent step or in the tetravalent stage. So, then if we are lucky enough, because we have to change the corresponding ligand site to stabilize the tungsten center in the pentavalent state, as well as a different ligand system for the tetravalent state. So, once we these 3 oxidation states we can make in our laboratory, we then again test it for their catalytic activity, and we can find that whether the corresponding catalytic site is active for the corresponding reaction. If we just simply take the corresponding hydration reaction of the acetylene, that the tetravalent state is active for the generation of acetaldehyde from acetylene, or the hexavalent state is active for the generation of the acetylene hydration reaction to give you the corresponding acetaldehyde. So, this will show, we will just see from in our next class that we can have a bidentate ligand, say MNT, what is that MNT and how this can be formed. So, L2, this fragment, that means metal is to ligand ratio ML2 system is preserved, that Ml2 is in our hand and is a sulfur bearing ligand, and tungsten is in tetravalent corresponding tetravalent oxidation state is prepared, and we get a corresponding tetraethyl ammonium salt, and that is therefore utilized for the corresponding transformation. So, next day we will see how these model compounds can be utilized for the corresponding catalytic activity. Thank you.